Thanks for the introduction. I'm an academic, but unlike most academics, I like to pride in myself that I try to do academics and teaching and research that is useful. So I actually want to build stuff. But it turns out that it's actually really hard to do this, especially when you're trying to impart this in your students. So the title of this talk might as well have been, how do you use some of the cool technology and tools that are being developed in the Python, in the SciPy community in particular, and convince your students to use them and actually get amazing stuff done with these tools that I'm going to share with you. So essentially what we did is I'm teaching this class that is called Engineering Sciences 155. It's the biomedical signal processing course. So the main portion of the course is about signal processing and how you apply that to biomedical data. And traditionally, the way this is taught is in a very dry manner. So this is deriving equations on the board, perhaps going over a few toy examples with the students in private. Now, I wanted to bring in a component where, rather than just talk about math and show the students how to do math, how do we tie up the technical component of my course with data that is collected from wearables that we give to the students, but now how do we allow the students to, in a very seamless fashion, process data and actually answer interesting questions of their own. It turns out that this is not easy to do if you don't enable the students with the right tools. And what I mean by the right tools is, say you have 20, 30 students in your class, you don't want to be worrying about having to install the right packages in every student's laptop and so forth. You want the students to have a very seamless way of interacting with the system that they're going to be using so that they can worry about the science part and not about this thing that software people worry about and that are great actually, which people like me leverage. So ES155, that's the short name for the class. So what is this class about? It's about bridging what I call the gap between how traditionally electrical engineering and other kinds of engineering are taught and computer science. So I'm an electrical engineer and mathematician by training. Now, traditionally, data collection and data sets, at least in my mind, are the realm of electrical engineering, while the processing of it, the storage of it, and the sharing of it through the internet is traditionally the realm of CS. So what this course was about is how can you bring these two worlds together by leveraging technologies such as Jupyter notebooks, Docker, and IPython notebooks on the cloud. And a representative discussion that I actually had with one of my students who asked me how I came about developing this course was, so I was telling her about how my frustration when I was learning signal processing was that it was not very tangible. So you're deriving equations and you're doing all of these things. And this is actually what led me, when I finished grad school, to learn all of these scientific computing tools within the Python ecosystem. And my student said, so what you're actually telling me is that you wish you had taken your class from yourself when you were an undergrad. And the answer is an emphatic yes. This is precisely what this course was supposed to be about, and she got this without me actually having to explain it. So let's go through, so rather than telling you what the syllabus of the course and what I teach the students and so forth, I actually want to go through examples of a couple of notebooks, Jupyter notebooks that were students authored, and that to me are actually pretty amazing, given the amount of time that the students had to actually author these notebooks. So hopefully this works. So the first notebook that I want to go through is a notebook that was authored by a junior, Dominic Vaux. She's a biomedical engineering major at Harvard. So Harvard has this weird thing where they don't call majors, they call them concentration. So she's a biomedical engineering concentration. And Dominic was interested, so the reason why I picked this notebook first is that, so at the onset of the class, what I told the students is that, hey, I know lots about signal processing. I'm excited about doing useful signal processing so that at the end of this course, whatever you will come up with can be shared with the world. And that was that. Now, what's interesting about Dominique is that she's the one student that from front to end, when it came to her project, did the project work in notebooks and actually authored a final report that was a notebook, which is sent without having been prompted. So the students actually sent us email asking us, hey, how should we submit these project reports? And on purpose, we didn't tell them anything. It turns out that Dominique actually got the message of this class, and the final output of her project was a notebook. And she actually did a very cool project. I'm not going to bore you with the details of the notebook itself. I have a link to the slides, and at the end of the slides. But she was interested in comparing different methods of assessing sleep quality. So your typical wearable would output some metric of how well they think you've slept over the night, typically using accelerometer data and other data. Now, the interesting thing actually about these wearables is that except for the one that we're using for my class and which costs about $2,000, these devices are actually closed data. In other words, you do not own the data that is being collected through these wearables. And all that the companies that are actually doing the processing on the data are sharing with you are these average metrics. And the interesting thing about this particular device that we've been using is that we actually have access to the raw data that is being collected from them. So Dominic was interested in devising an algorithm to assess sleep quality and to compare it to Microsoft Band's algorithm and an algorithm from a popular phone app. And she actually came up with a very interesting project where, so as you can see here, this was her experimental setup. So she had the band from the class and the Microsoft Band on one wrist, her phone running the sleep app, and actually a Microsoft Kinect camera. And the use of the Kinect camera is motivated by the following. So from the bands, you can actually get raw accelerometer data. It turns out that different sleep states correlate with motion through the night. And one interesting idea we had was that, hey, you could use the infrared sensor on the Kinect camera to actually detect motion and correlate that with the motion detection you would perform from your accelerometer data and essentially do a validation of how well one can detect motion using the accelerometer data. So the details on the notebooks are in the link that I'll share with you guys. But basically, this is what you would expect from a notebook where you have both data collection, an experimental protocol, data analysis, and the use of very sophisticated algorithms to detect motion. So I'm not a Mac person. How do I get out your viewer? How do I go back to the slides? Okay, thanks. So the other notebook that I want to show you, and hopefully I can get back to the slides after showing you this one, this is actually almost my most favorite of the projects. So the interesting thing, once you actually put these tools together and package them and put them in the hands of the student, is that they come up with ideas that I would not have come up on my own. So this is a project by two students, Ryan Halverson and Carly Zlatic, both of them athletes, and Ryan is in the varsity football team, Carly is in the varsity soccer team. So they actually came up with an interesting project, which is how can you use accelerometer data collected from the wrist of a shooter to actually predict whether a free throw shot in basketball is going to go in or not. And what's really interesting to me about this project is that the actual content and the matter of the project was motivated by the fact that these two students who are athletes actually came up with something that is based on their own experience, and the fact that, for example, Ryan has 2 or 3 roommates who are on the varsity basketball team. So he actually went through the process of going with his friends on the basketball court, shooting, having them do shots, manually collecting whether the shots went in or not, while they're simultaneously wearing the band. And in the case of this particular project, so if you're a fan of the NBA, why is this relevant? So this is actually not just for fun. This is relevant because if you look at the league average in the NBA, perhaps over the past 40, 50 years, of a made free throw, it's been steady at about 70%. And there's some interesting cognitive science and neuroscience research that shows how one can use enabling stimuli, basically such as when you're training your dog to learn certain actions to enhance performance of athletes and to enhance performance in general. So imagine a setup where you could have somebody wearing one of these devices and an algorithm that predicts whether the ball is going to go in prior to the shot actually being made, and you being able to deliver stimulation that would reinforce their performance. So this is the kind of future we're predicting, and it's not too far off. And there's actually a very cool video that Ryan made, and at least as far as I know, this is the first time we know what the signature of a basketball shot is through accelerometer data. And these are not ideas that I came up with. This is something that Ryan came up with on his own. So over here, this is the basketball shot. This is when he flicks his wrists and the shot goes. So it would be really cool if before that moment, you could actually, so right here, this is the shot. It would be really cool if, and the resolution here is about a couple of seconds, so the shot itself is a few tens to a few hundreds of milliseconds. It would be really amazing if you could design an algorithm that could actually predict the outcome of the shot from here. So these students were given about 4 or 5 weeks to actually work on this project, and actually did an amazing job based on that time frame. In this particular project, we did not get to the prediction, and it's something we're actually working on at the moment. So moving on, other projects that students did. So there was a project that actually tried to use, again, experience-based. The idea was, these are busy undergrads that have a lot of things going on. Can you actually use devices from band to predict what kind of stresses you have in your daily life and accordingly make changes? There was another project that's very interesting, in some sense motivated by Mission Impossible, and this project was about, can you actually use accelerometer data to identify people using their gait? So there's this idea of an eigenface in computer science that a lot of people might be familiar with that is actually used heavily for face recognition. The idea here would be, can you actually collect data across a significant number of individuals and do some magic and actually extract what the signature of a person's gait is. Imagine walking through your house's door without actually having to turn a key, but having an automatic signal that goes from the band sitting on your wrist to something that unlocks your door. So this was the motivation of this particular project. There was a third project that was about sleep analysis and sleep quality analysis. This particular project was focused more on actually being able to determine different stages of sleeps. It turns out that this is really hard to do if you don't have access to electroencephalography data. And last but not least, an interesting project was about correlating band data, thankfully I'm not wearing a band at the moment, with the quality of a speech that is being delivered. So I'm going to breeze real quick through the backend or the infrastructure that supports this. A lot of the people attending SciPy actually have done a lot of the legwork that we used to design the backend that the students could connect to and use the system seamlessly. So what's happening here is that we're on AWS, and there's a website that the students go to, connect to an AWS load balancer that sends them to Jupyter Hub, which is running on an AWS EC2 instance, and there's a redirect that goes to GitHub. Now, after this redirect, student logs into their GitHub account, Jupyter Hub connects to a Docker spawner and asks it whether the student actually has a Docker container in there or not. If it does not, it creates one, stores it in a database. If it does, it serves a notebook to the student. And so apologies for the lack of acknowledgement here, but there's a few people attending the conference that should be acknowledged here for the motivation of how we actually developed our system. No, I did not mean to do this. So this is just zooming in on what that process is. So this concept of a lab in the wild, and if you're old enough, you would recognize where this particular play on word comes from. But this is actually a concept that was coined by Yasha that is sitting up front here. The idea being that, so how can you have full vertical integration of data collection? In our particular case, using this device that I'll introduce in a bit, is called the Empatica E4. It's the $2,000 wearable. How can you have vertical integration of data collection, sophisticated signal processing and data computation in the cloud, and something we did not get to in the class is the use of the Internet of Things, meaning using the output of the algorithms that may be running on a server or locally on your machine to enact some type of an action. So this Empatica E4 is what I call the Mercedes-Benz of wearables. So one of the frustrations that we had when actually designing the syllabus of the course or implementing this particular idea, it turns out that, and I'm happy to talk to people that might know about this, it turns out that as far as we know, this is the only device out there for which you can have access to the raw data. This is the only band out there for which you can have access to the raw data. And it sort of justifies the reason why it costs about $2,000 to have one of these devices. So basically, what this device allows you to do is continuously record 4 different modalities of signals. You have a pulse oximetry sensor that uses light to essentially come up with an estimate of your heart rate or of your blood volume pulse. Because as your heart beats, basically, the conduction of red light through your bloodstream or light of different wavelengths changes. And you can use this to essentially detect something that is akin to an EKG, but not exactly. There's an electrodermal response sensor. So what's the electrodermal response? So as you go through different emotional arousal states, it turns out that your sweat glands emit these very minuscule sweats, basically. And you can detect the change in resistance in your skin that is due to the emission of sweat through the skin. So the third kind of sensor that you've got here is a temperature sensor that is useful, for example, if you would want to determine the circadian clock of a given person. And last but not least, which is the sensor that was the most used in some of these projects, is an accelerometer data sensor. So how do you manage the course? We're on Bitbucket, and the reason why we're not using GitHub to store the student data is because of privacy regulations. There's this rule that is called FERPA that essentially treats the notebooks that are being authored by the students as assignments that are graded by the instructor and for which the student is entitled to a certain level of privacy. But in the future, we'd like to have full integration of not using Git for the login and then Bitbucket for storing the data. We'd like to have a full integration of this. So we own a team, a Bitbucket team, that's called ES155, and we use it for course development, for managing homeworks, labs, and course materials. Some of these data, the student have both read and write access to. Some of the other data, they only have read access to. And so to conclude, what are some of the key lessons that we learned from this class? And I'll let Diana and Yasha chime in when it comes to the QA portion of this talk. So one of the things that I learned personally about this experiment, and that I was actually a little sad about, is that once you empower the students with the tools to actually go and be able to do their own thing, it's as if I, as the instructor, actually don't exist anymore. They don't come to my office hours anymore, or they only come when they're stuck. Which is great, but one of the things that was very important in the course is that you empower the students with these tools, and they're actually very powerful tools that, put in the quote-unquote wrong hands, might lead to very dangerous and interesting things. It turns out that once the students have access to the tools, they come up with these very wild ideas that are not necessarily realistic. So my job as an instructor is essentially to let them know what the correct playing field is for the amount of time we're given for these projects. And in a future instantiation of this class, actually, given these tools, I'm thinking about switching to a more project-based course, where very, very early on, the students actually start working on a project and using lectures in class essentially to fill up a few holes here and there in their technical knowledge. And I would be preaching to the choir here with the second point here, which is, I think that in the future, literacy, so fluency with data, or being able to manipulate data, is probably going to be part of literacy. And this is something that is being done in a data science-like course, a biomedical signal processing course. But what I would like to see is, at undergrad institutions in general, a student taking a government data course or a government policy course, actually working side by side, a government policy professor working side by side with somebody like me or a computer science professor, and data from the government are out there, their data resources. How can you actually use these tools to make data-driven decisions or have students perform data-driven inquiries? And again, there's a huge impact for education. And another thing we learned was that it turns out that the students, most of them primarily use the platform as training wheels. So what you have to understand is that the students for who this is targeted are not your typical computer science savvy students. So for those particular students that were in our class, we didn't need to teach them anything about version control, about Jupyter notebooks and so forth. But for those who are not, using these tools in a class relies heavily on things such as the notebook and the cloud, because at the beginning of the course, they can just focus on getting the things done rather than learning the technology itself. But it turns out that as the class progressed, and especially as the students, as some of the projects required more and more computational tools, they were actually able to transition to using data locally on their own machines. And so with that, this is the end of my talk. And you can check out these projects at the following links. And I'd like to acknowledge my core staff, two of whom are here, and as well as the organizers of SciPy 2016. Thanks for your attention. So, yeah, I got the question. So the question is the wearable that we're using for the class better than a Fitbit, or is it just that we have access to the data for this particular wearable? So it's an interesting question because it depends on what you mean by better. So one of the things I've learned by digging into these wearables and how to use data that's acquired from these wearables is that actually physicians don't care about, your doctor does not care about your Fitbit or your Jawbone. So if you come to your doctor and tell him that, hey, look, I've been having these symptoms and I've been collecting data from myself, can you take a look or what do you think? They're just not going to care. Now, why am I bringing that up? I'm bringing that up because it's actually, we do not actually know scientifically yet how much medical value is there in data that is being collected by these wearables. So for example, this particular device we're using, for heart rate, for example, well, I mean, our heart beats at about what, maybe once every second on average. So which means that if you had a sampling rate of about 2 hertz, you'd be okay. But for example, this device has a sampling rate of 64 hertz for heart rate data. How much information is contained in that actually has diagnostic value? I don't think anybody has the answer to that. So we don't know if it's better. I suspect that it is because of the rate at which the data are being collected, but I don't think anybody has actually scientifically shown what value any of these devices have. Yeah.
Hi, do you still teach theory in your class?
So that's the interesting thing, and I can also let my course staff answer this question. But the interesting thing is that's been one of the challenges. So I'm a proponent of not having to dilute the theory in the service of doing something cool. So we actually significantly teach them theory. So one of the things that's been challenging is how do we balance teaching them theory and actually having them do technical problem sets with also giving them assignments that are more practical. So this was the first time we taught the course. And I mean, what my course staff told me is that the students were actually hammered. So so they were really excited. We got really good feedback about the course, but there's a question as to how much balance, where is the right balance between teaching them theory and actually doing interesting and cool stuff?
Does this work? Yeah. So I just had a quick question. It sounds like the course kind of has a fair amount of moving parts to it. And I was wondering if you've thought a bit about how you would try to scale it up if you got, 2 or 3 or 4 times as many students interested or something like this.
So can you elaborate a little bit on moving parts?
Well, I mean, you showed like an org chart basically with like a bunch of people that were already involved in the course, and you have hardware that a lot of people are utilizing for the course, and there's also just the pedagogical challenges of teaching more people. And I just wonder if your hope is to scale it up, given that some people may not, it is sort of an intro-ish course to some people, it sounds like. Mm-hmm. What are the ways that you could imagine doing something like that?
So on the data collection end, I think the main barrier is the cost of the devices. And actually, Yasha, who is here, is part of our hardware team, and we're actually working on building our own. And but as far as the data processing is concerned, so there's still a lecture component. So however many people we have in the class, they still have to attend my lectures and learn some of this material. As far as the data processing component is concerned, I think that is, at least as far as I'm concerned, I think this is solved by this technology, basically. I think the Berkeley folks are giving a talk tomorrow about their use of Jupyter Hub and using this to teaching thousands of undergrads data science. So the processing component, I think, is solved. I think what's not solved is the data acquisition component, specifically with the wearables. So where I would really like to see this course go is to be a course actually that's both about hardware and the data processing. So I'd like students to come into the course and essentially have an interesting question that they want to answer in mind that requires them to collect data, build the hardware for that themselves, but with the data analysis in mind, and actually go through the whole pipeline. That would sort of take care of that, because then they'd be responsible for building the hardware. But I don't think it's too hard to actually scale this. So what's probably going to be hard is, going back to the question about theory, is, okay, now that I have this many students, then can I teach them all this theory without having to blow up the size of the course staff? But I'm happy to talk about this offline and see if you have any thoughts.
There we go. This was a great talk. Thank you so much for sharing this. I think you probably said this, but I missed it. I was just curious, like, to what extent do your students have experience either with programming or, I'm just curious, like, what their background is when they come into your class.
So Yasha, Diana, do you want to take this?
So of the tune-up of such Dominique came into the class with a very rudimentary understanding of programming. She was a MATLAB programmer, and a lot of things don't carry over. Ryan was also a MATLAB programmer, and Carly was also a MATLAB programmer. And you see a lot of weird constructs in their code that carried over. By the end of the course, they seem to have really, really picked up a lot of the basic Python structure, and they can go out into the world now and actually write code. So it's really a 0 to 60 that they went through in a semester.
Yeah. So this might be cheesy, but I mean, this course was essentially a selfish way for me to try to empower my student, because one of the frustration was, hey, we're sending out all these kids into the world that know a lot of sophisticated tools, but come out just knowing how to program in MATLAB. I hope there's no MathWorks people here. MATLAB is very useful, but as people in this crowd know, is if you're thinking about using engineering to actually build real systems, right, it just does not cut it. So this was about how do you actually empower the kids to do that, and I think we've done that fairly well. Happy to take suggestions also.
Really impressive, thank you.
Thank you. Oh, there's.
Okay, so we can keep asking questions. We should probably start to switch out the video systems so that Brian Granger can come on. The next talk will be here in 5 minutes. We have Brian Granger talking about Jupyter Lab. But again, please keep answering questions if you're willing.
Just a really quick question. Did you notice any sort of pattern between the people who chose to work on their own against the people who chose to work as part of a team? I would expect that the people working as part of a team were able to get through a new set of tools like much quicker and like having more fun maybe.
So it's interesting. So the first notebook I presented, Dominique, which was the notebook that I thought essentially captured the vision of the course, she worked alone. And it was my favorite project. And she was an undergrad. The other person who worked alone was a grad student. So you kind of expect that. They want to be left to do their own thing. And I felt that that project was actually subpar compared to the project that Dominic did. I think it's really about, and I had to go through this when I taught myself these tools. So they're great tools, but there's a certain amount of barrier to entry that I think this community and a lot of the tools that I've heard about here are making much, much more seamless for people. And once they learn them, they just go. Yeah. Thank you.
Okay, so we have. Thank you.